Hello, everyone. Today, I'm going to be giving a general overview of that much maligned science, physical chemistry. So everyone's probably heard bad stories of physical chemistry, but I want to essentially take this as a chance to give an overview of what it is that physical chemistry is addressing and why it might be one of the more important sciences that you can pay attention to. And so the classic description of physical chemistry is it's a way to more or less apply math to almost every observable thing you see. But I like to take a little bit of a step back to kind of a wonderful moment by a Nobel Prize winner, Richard Feynman. So many of you may know this as the bongo playing Nobel Prize winner, who really did a good job of popularizing a lot of physics. And one of the ways that he started his description of physics was essentially by asking the question, so if all scientific knowledge were to be destroyed and pretty much civilization ends, and you have only one sentence that can be passed on to the next civilization, the next generation, and at this point, this might be a very reasonable question to ask. What is the single sentence or statement that you could pass on that would contain the most information in the fewest number of words, so the most information dense, that would give the best chance of getting the entire field of science started on the right foot? And I really love what his proposed answer was. And we're going to be spending a lot of time dealing with this sentence. So he proposed more or less the atomic hypothesis. So he essentially said, all things are made of atoms, which are just little particles that move around in perpetual motion, so never stop moving. And they can attract each other when they're a little distance apart, but repel each other if they're squeezed a little too closely together. And one of the reasons I really love this single sentence is this single sentence is physical chemistry. We're going to be using these concepts either directly or kind of implicitly all semester, and in fact, all year. And from this single sentence, we can extrapolate almost all of chemistry and most of the physics that we care about. And I really kind of want to take a little bit of time, starting with these basic principles and just building up in a conceptual sense what we're going to be talking about all semester. So let's go ahead and start with this idea that all things are made of atoms. So we know that atoms can make molecules. So if I'm just look at a molecule, I know that it's going to be in perpetual motion. So here's my classic CO2 molecule. And so it's going to be moving perpetually. And one of the easiest way it can move is by essentially having some of its energy or motion moving in the three cardinal directions. So X, Y, and Z. So using this, it can go ahead and bump into things. And we're going to be starting this semester by looking at a lot of this translational motion. But it turns out that it can also rotate. So it's got 2 degrees of rotation. It can essentially either rotate end over end, or it can kind of do a barrel roll about its principal axis. And so this gives us 2 degrees of rotational motion. And this is going to take in some of that constant motion. And each of these types of motion will have slightly different implications as we go on. So if I'm looking at a non-linear molecule, so let's take a look at, say, something like formaldehyde, where I now have still a fairly simple molecule, but it's no longer along a straight line. Well, it's still going to have its 3 translational degrees of motion, but now it also is going to have 3 rotations. So it can either rotate this way, it can rotate end over end this way, so where the oxygen would end up over here, or it can essentially rotate about this axis where my 2 hydrogens are the only thing spinning. So this gives me 3 degrees of rotation. So if I've got a nice linear molecule, I've got 3 degrees of translation, 2 degrees of rotation. And if I have a non-linear molecule, I've got 3 degrees of translation, always get these, and 3 degrees of rotation. You can also imagine a single atom, which would only have the 3 degrees of translation. And one of the really important things we can take home is that it turns out that these two types of constant movement are going to underlie a lot of the properties of bulk systems. So they're going to include a lot of things like diffusion of molecules, a lot of different types of spectroscopy. But it turns out there's one last type of molecular motion we can have. And that's the fact that it turns out that my molecules might actually be relatively standing still, but the atoms within them may actually be moving with respect to each other. So this gives us our classic vibrational motion, where I can imagine that my oxygen and carbon can come together and then move apart, and come together and move apart. And this really goes back to that statement of Feynman. They want to get a little bit close together, but if they get too close, then they repel. And this underlies a lot of this kind of atomic motion. So I have my molecule being able to move as a whole, either by translating or rotating. But it also turns out that even if it's relatively standing still, the atoms with respect to each other are going to have their own degree of vibrational motion, which in a simple case models a lot of kind of this translation-like behavior. And we can do this in an energy diagram. So what we essentially see is that the atoms are most happy when they're at some sort of equilibrium distance. If they get too close, I run into a repulsive potential. And if I get too far, well, then it turns out I'm decreasing my attractive potential. And so I'm going to want to stay somewhere in this range, moving back and forth. We often model this as a simple parabola, but it's a little bit messier. So one of the big things that's worth noting about these molecular vibrations, which again, we tend to monitor using infrared spectroscopy, so that's the vibrations that we look at in IR, is that it turns out that, let's say I give this molecule too much energy. So if this molecule has too much energy, then this carbon and oxygen can essentially start bouncing back and forth in this well, so much that eventually I'll have enough energy to go out here, at which point I disassociate and I get two separate smaller molecules. I get an oxygen atom and carbon monoxide. So again, this is one of the tricks that you can have that can lead to real chemistry, breaking and forming of bonds. Similarly, you can also imagine there might be something I can do to weaken the strength of this bond by essentially making it easier to dissociate. So if this well ends up being too shallow, even if I have the same amount of energy, it's going to be easier for molecules to break apart. So this is going to underlie a lot of this kind of bond breaking and forming that we see in real chemistry. So one of the things is that I might not just be looking at a single molecule moving or breaking apart. I might actually look at what happens if I've got two different molecules that might be able to interact. And so what we can do is look at what happens if I've got two chemical species that are going to be separate that can physically approach and make a new product. So I can start with some reactants like A and B, and there may be a third molecule some far distance away of C. So what we see, so here, what I'm looking at is the AC distance. So it turns out that B and C distance. So C might be able to approach B till it reaches some critical point where it's almost happy, at which point now A is too close because it turns out that B can't stand to be too close to two things. And so then A can disassociate. And so what we've done is we've taken that same basic parabolic model that we had for a single atom, and we just added an extra little nuance to it. And so what ends up happening is that it turns out that if you have a relatively low barrier, so this point of highest energy, where I try to get all three of my atoms close together, if this is low enough, then it's possible to go from my reactants to products and have a real chemical reaction. I start with one thing and I end up with a different set of molecules. And one of the real big tricks of chemistry is going to be looking at the favorability of this reaction. And we tend to do this using two classic metrics. So this is going to be the energy of my reactants versus products. And so this will essentially give me the equilibrium of these two, of this reactant versus product state. And then turns out that my products may be favorable, but I have to make sure that this transition state is low enough that I can have ready movement between the two molecules. And so it turns out that if what I mostly care about is my reactants, products, and the transition state, we can start generating full energy surfaces or curves for more complex reactions. So again, what I did is I just took a diagram out of one of my recent publications where we have some species. It's an exo of an exo species, which essentially just refers to the stereochemistry of this hydrogen, around what's called the Troger's base. And then we look at essentially the removal of that hydrogen, and then the energy of, say, that hydrogen being on the other side, or the other stereoisomer. And so what we can do is get the energy of each of those given states, including the transition state, and start to figure out how likely am I to be in one state versus another? How likely am I to deprotonate? How likely am I to go from this initial species to the deprotonated species? So using all of these relative free energies for each of the chemical species, then we can start getting a lot of information about what's going to happen on kind of this bulk level. So we can start really mapping out what will happen chemically. And this actually is really exciting, being able to make predictions based on the simple behaviors of individual atoms or molecules. And again, it turns out that really what we're going to be focusing in on is not so much will something occur, but about the relative probability of something occurring. Because one of the things I'll often bring up is that when we're dealing with molecules, we're dealing with vast numbers of species. So we're simply looking at the probabilities or what percentage of molecules made a certain transition. So it turns out, yeah, we can use all of this various energy information to essentially describe the composition or what percentage of a solution is in any given state at any given time. And this gives immense amount of predictive power that really will help underlie almost all of the rest of your chemical knowledge. So this is more or less the course we're going to be trying to follow throughout this year. So our first semester is going to be in Physical Chem 1. So what we're going to specifically focus on this semester is this idea of movement and energy, both of molecules and atoms, and how we can turn these ideas, especially of energy, into real chemical phenomena. So the first thing we're going to want to do is look at how I can describe energy, most specifically of gases, and relate it to essentially physical properties that I can measure, such as temperature and pressure of a gas phase species. So we mostly do this of gases because they're relatively simple and easy to work with. Then what we can start doing is build up several different models of energy that will give us slightly different pieces of information about the behavior of our gases. Then once we have a good knowledge and understanding of how gases behave and certain favorabilities of movement and changes of the system, we can start to expand this to liquids and solids and even the transition between these three, which essentially acts as almost the simplest form of a chemical reaction. Then using this, we can try and extend it to actually full chemical reactions. And this will tend to happen by about the end of the semester. And once we have an idea of what energy tells us about the equilibrium composition of these chemical species, of who's favorable and who's not, we can start finally examining this idea of rate. So this is going to be the major focus of this semester. Next semester in P-Chem 2, if you stick with me, we're going to really be focusing more on these beginning ideas of kind of these atomic level interactions and behaviors. So the behavior more specifically of atoms and molecules on a very kind of small scale approach. And one of the reasons we often wait for this is because this is going to involve a lot of quantum mechanics. Because if I'm going to describe the behavior of electrons and nuclei, which is really the fundamental driving feature of chemistry, I'm going to need quantum mechanics to do that. Then once we have an idea of how electrons and nuclei behave, we can start scaling this up to the behavior of molecules. So specifically to things like translational, rotational, and vibrational motion. And then as we kind of showed, once we have a good grasp, especially of vibrational motion, we can start relating these into interactions with light into spectroscopic measurements, which will give us specifically microwave and IR spectroscopy. And we'll also see certain electronic movement, which exhibits itself as UV vis spectroscopy. So this gives us a lot of those spectroscopic handholds that we often like. And then, using what we know of vibrational motion, we can start building up a lot of atomic and molecular properties, especially getting into these ideas of stability of the molecule and beginning to get back into how can I predict whether a reaction will really want to occur, more on this atomic scale. So this is more or less the direction we're going to be trying to take the class this year. I hope you stick with me. We're in for a wild ride. I'll see you next time as we describe the behavior of gases. Take care until then.